Welcome, ladies and gentlemen. My name is Brian McLogan, and in this video, we're going to work through the unit circle. This is the fourth lesson in my unit for trigonometry. So again, I'm going to work through my notes, so therefore you can get an idea of what the unit circle is, as well as how we're going to use it. And this is a very, very important lesson because from this lesson on, we are going to be referring to the trigonometric functions most often using the unit circle and no longer with triangles. So basically we're going to come through is where do the points on the unit circle come from? How do we find a point on the unit circle given an angle? And how can we evaluate the 6 trigonometric functions given an angle? So you can see here's the difference here. Previously we always had to evaluate the 6 trig functions with a triangle. Now we're going to be using a circle, which kind of seems weird, but hopefully through the end of this lesson it will make a little sense to you. So to kind of set this up, in our first lesson, we talked about special right triangles. So here's an example of 45, 90 degree triangles, all right? And these are all the side lengths, because again, remember they are all proportional to each other, right? So all I did was I took these triangles and I just multiplied them by different scalars to kind of get these triangles. So the sine of 45 degrees is the same. We know the sine of 45 degrees from day one is square root of 2 over 2. And you can see, do opposite over hypotenuse of any of these triangles, and you're going to simplify to square root of 2 over 2. Now, on day one, we had some problems that we wanted to evaluate for the, sine of 45, cosine of 45, tangent of 45, and we want to do all those. So we said, which side lengths would make this the easiest? And on day one, we decided that triangle C was going to be the easiest because it had the two legs were 1 and 1. And for that day, probably it was the easiest based on what we knew. However, what we're going to use today is the 45, 45, 90 triangle where the hypotenuse is 1. And that's the essential understanding that we need to take away from today, is that this hypotenuse is going to be 1. And this is actually going to make our life easier and make everything possible that we want to do. And the reason being is because if you took sine of 45 degrees, you're going to do opposite over hypotenuse, right? Well, if you have opposite over hypotenuse and your hypotenuse is 1, we don't really care about the hypotenuse. We can just look at the opposite side. In the same respect, adjacent over hypotenuse, if it's over hypotenuse with 1, just go ahead and look at the adjacent side. So this helps us a lot when understanding our trigonometric functions. We don't have to do this opposite or adjacent we don't have to look at that full ratio when we know the hypotenuse is 1. And we did the same thing for the 30, 60, 90 triangle. Again, same thing. Here's all 30, 60, 90 triangles. They're all proportional to each other because obviously we know the sine of 30 degrees is 1/2, right? And you could do opposite over hypotenuse, right? Or you could simplify these. But in this case, you notice that it's 1/2 over 1. You could say, oh, the sine of 35 degrees is just the opposite side, right? When the hypotenuse is 1. The cosine of 30 degrees is, just square root of 3 over 2. I didn't even have to look at the hypotenuse because it was 1. And that is again, really going to be our focus today, is only working with triangles when the hypotenuse is 1. All right, so last class period, we talked about the constraints and how it mattered which quadrant a triangle was in, because previously, we just dealt with these triangles that were just in space. You could have a triangle, 45 degree triangle like this. And we're like, all right, there's a triangle in space. But then we talked about, well, if we have these on an XY axis, then the side lengths can be positive or negative. So if you look at this first quadrant, right, if we take this triangle, you can see there's my triangle I talked about. The adjacent side is square root of 2 over 2, square root of 2 over 2, and 1. Now, obviously, if it's in the first quadrant, everything's going to be positive. But we could also think about this, well, it's on a coordinate grid. We could take this to be the coordinate point, square root of 2 over 2, comma, square root of 2 over 2, right? From the origin, you're going over square root of 2 over 2, and then up square root of 2 over 2. So again, this is that special triangle that we are referring to. But rather than that triangle just being randomly in space with no orientation, we're putting it on an XY axis. So a couple key measures that we want to make sure we understand here is 45 degrees is the degree form, right? And we're familiar with. But since we've also talked about radians in day 2, we know that's equivalent to be pi over 4. And again, notice that we're using this central angle, right, with the origin, and it's going to be perpendicular to the x-axis. Now, if I take this triangle and I reflect it about the y-axis, notice that really the only thing that changes is the x-coordinate, right? Now we're in the second quadrant. So the x-coordinate is going to be negative. The y-coordinate is still positive. the hypotenuse is still going to be 1. The central angle, or what we call the reference angle, is still going to be 45 degrees. Now, this is where it kind of gets a little confusing. Where am I getting 135? Well, again, like here's this angle. What we're really kind of measuring is this angle. That's what I'm writing down right there. And you'll see how we write that out. Basically, what I'm drawing is the angle from the standard form from here to here. That's what I'm writing there. Because we know the reference angle is 45 degrees, 45 degrees, 45 degrees, right? But if I wanted to figure out what are the actual angles from standard form that are producing those angles, that's where I'm getting those measures. Okay, so that's what I'm calculating, the 215 degrees, 5 pi over 4, 315 degrees, 7 pi over 4. And again, basically all I'm doing is if I know this angle is 45 degrees, and I know halfway around a circle is 180, I subtract 45 to get 135. I add 45 to get 225. All the way around the circle is 360, subtract 45, that's going to be 315. That means the angle from here to there is going to be 315 degrees. Now it's important that you understand like that angle from 315 degrees, right, is really equivalent to like negative 45 degrees. They both produce this terminal side, which yes, obviously makes this triangle, but it produces also this point. Square root of 2 over 2, negative square root of 2 over 2. Because if I take this triangle and reflect it about the x-axis, you can see that this is going to be a negative, that's going to be a negative y-coordinate. In the same respect, if I take this triangle and flip it down to the third quadrant, you can see how both of these points are all going to be negative. Okay? And that was basically it that I wanted to cover with the 45-degree triangles. Making sure that, again, the same thing, halfway around circle is 4 pi over 4, right, which is pi. So I'm subtracting pi over 4 to get 3 pi over 4, add pi over 4 to get 5 pi over 4. All the way around the circle is 8 pi over 4, but you can see that this angle right here, right, all the way around the circle is 8 pi over 4, but you're pi over 4 short. So that's why I came up with the angle 7 pi over 4. And I know it doesn't really, it kind of seems a little confusing. In my class, I gave the students actually the unit circle to fill out with me. And I guess I probably should have mentioned that before. So therefore, they knew what to write in these angles, because these angles, like these angles right here, do not represent those angles right there. Those angles are all the same, which is 45 degrees or pi over 4. But what these angles represent is these angles up in there. And I guess I probably should have made that more clear. So hopefully you didn't get confused, because when I just started looking at it, I could see where some of you might have been coming from on there. But the main important thing is that we have a 45-degree triangle. These are not made-up triangles, right? We have investigated these triangles before. You've seen them, right? And we could have picked any one of these triangles, right? Any one of these. We could have done this one if we wanted to. But for the sake of today's lesson, we are going to stick with the 45-degree triangle where 1 is the hypotenuse. All right, so that's why I'm using this triangle in these 4 quadrants. I could have used any 45, 90-degree triangle. But by using 1 here, we notice that now the hypotenuse is 1 for all of them, okay? And then these are our side lengths. And then, just like we learned last class period, when we have the side lengths, we could also write them as coordinate points at these little points right here, all right? So now we have more than a 45, 90-degree triangle. We can also do a 30, 60, 90. So let's go and take a look at a 30, 60, 90. All right, so on the 30, 60, 90, what we have is basically, again, these little triangles up here, right? And instead of picking any of these, I'm just picking this one because it has a hypotenuse of 1. I'm trying to go with that theme of the triangle is going to have a hypotenuse of 1. So again, I'm doing the same exact process here. I am just orientating. I'm not really sure. I'm just making the orientation of the triangle to lie on the first quadrant where the 30-degree angle is at the central angle. Now, again, for the understanding of degrees and radians, I'm going to convert 30 degrees into radian form. You can see this is pi over 6. And yet again, no matter what I do with these reflections, I don't know why I didn't negate those. Jeez. No matter what I do with these reflections, these angles all remain the same, right? But again, like these angles right here are not the angles, the little central angles. Those are the angles for in each quadrant. So that's that one, that angle, and that angle. Okay, so 150 degrees. So again, if we know this angle is 30 degrees and we know halfway around circle is 180, you subtract 30 degrees, and that's how I get 150. right? Or you have pi over 6, 6 pi over 6, you subtract pi over 6, you're going to get 5 pi over 6. And that same process is what I did. I added 30 degrees to give me 210, or I added pi over 6 to give me 7 pi over 6. All the way around circle is 360, so I subtract 30 to get me 330 degrees. Or all the way around circle is 12 pi over 6, you subtract pi over 6 to give you 11 pi over 6. So that is the process from there. Obviously, the square root of 3 over 2 and the 1/2 comes from the triangle that I previously showed right up here. And then, again, like understanding, since this is on a coordinate grid, like an xy axis, I can write the distance from the origin here of square root of 3 over 2, 1/2. I can write this as a coordinate point, xy, right? And then as I'm following these reflections, we obviously know that in the second quadrant, x is going to be negative. In the third quadrant, x and y are both going to be negative. And in the fourth quadrant, the y coordinate is going to be negative. The hypotenuse is going to be 1 for all of them. And that's really the only thing that's changing, right, is that these coordinates are changing and that the angles are going to be different for each one of these. Yet, their reference angles are all the same. And that was kind of one of the connections I wanted to make with the students when we were creating these, is they all have the same reference angles and they all have the same coordinate points. The only thing that really changes is the signs of the coordinate points based on the quadrant that the angle lies in, right? Because the angles are different, right? All of these angles are different. So all of their quadrants are also different. And since their angles and the quadrants are different, that means the signs are all going to be different. Yet, the things that remain the same is the reference angles are all the same, the values of the coordinate points are all the same, and the hypotenuse is all the same. So those are some of those kind of similarities we wanted to do. But we kind of get stuck here when we only have a 30, 60, 90 and a 45, 45, 90 triangle, right? So we basically just took two triangles, threw them on the coordinate grid. Like, what else can we kind of do? Well, that kind of brings us up to our 60, 30, 90 triangle. We can also take a 30, 60, 90 triangle, right? Instead of doing this, 30 degrees, 60, we can just flip it. It's the same triangle. I'm just changing the orientation of that triangle. Right? So if you just take the triangle, flip around, like still the same there. And then again, so we now know these coordinate points. Again, the hypotenuse is always going to be 1. This distance here is what, 1/2? I'll just write that in there. And this is square root of 3 over 2, right? Just like we did for all the other ones. Did I write that in there? Yeah, I did. So this is 1/2, that's square root of 3 over 2. Now, in this case, we have 60 degrees, right? So we convert that to radians, and that's going to be pi over 3. So these are all 60 degrees, or pi over 3. So again, if halfway is 180, subtract 60, you get 120. Add 60, you get 240. Halfway around a circle is 3 pi over 3. Subtract pi over 3, you get 2 pi over 3. Add 2 pi over 3, you get 4 pi over 3. All the way around the circle is 360. Subtract 60, you get 300 degrees. Subtract pi over 3, you get 5 pi over 3. And again, just for the sake of conversation, or when students are looking at this at another date, I just want to make sure students understand those angles. That again, the measure here that I'm giving them is not for the reference angle, because we already know the reference angle is the same, but it is for these angles here, which produce the same terminal side. All right, but we're going to make this connection between these reference angles and these angles that I'm providing you, and how they relate to each other. All right, so then the hypotenuse L1, we do our reflections, just make sure I did the negatives in this one correct, which I did. And again, you can kind of see it's the exact same thing now. We're just putting a 30, 60, 90, we're just rotating. So it's the same triangle. So in reality, I haven't really done anything new yet. All I have done is taken two triangles that we've already investigated in this class. I have changed their orientation and I've put them on an XY axis. Right? Now I did selectively choose the right triangles when the special right triangles when the hypotenuse was 1. But that's about it. So what if I took this quadrant, put it on top of this quadrant, and then put it on top of that quadrant? Right? You would have 12 triangles on a quadrant. And that would look a lot. And you could probably look at this and say, wow, that looks really confusing, especially with all the writing I would have, right? But that's exactly what we want to do. And what happens is when you combine these, I'm just looking at the first triangle here, but when you combine these, yeah, you're going to have, these 12 quadrants here. But what's nice about this is you can see when you put them together, they create this nice little curve. And again, Also, going with that understanding of the hypotenuse, or the distance away, the hypotenuse is 1, you could say, well, from here to here is going to be 1. And if there to there is 1, and then if you just connect them, you can see it makes that beautiful, nice little arc, right? And then if you kind of continue that arc, you can see it brings up a circle. And that's what we call the unit circle. And again, why do we call it the unit circle? Well, we call it a circle because obviously it creates a circle. And it's the unit circle because like our counting unit is by ones, right? So it's the radius is 1 of this circle. And that is because we chose the triangles to have a hypotenuse of 1. Right? So we could use if we would have chose the hypotenuse to be something else, then we could call it a something else triangle. But 1 is going to be our preferred number because it's going to make our life a little bit easier once we get into our trig functions, which you will see in a second. You can see here by looking at these 12 functions, that's going to be a lot of triangles or points to remember. So like, do we really need to memorize all of this stuff? And the simple question is no. I just want students to basically memorize these coordinate points, basically the first quadrant. If the students know all the points in the first quadrant, then they're good to go. And again, there's a lot of ways to, memorize the quadrant. Obviously, you can look at your hand, like a lot of people know the good old hand method. Like you have 5 fingers, and how many points are there? Right? There's 5 points. So that's an easy way to remember them. The first 2 points are easy to remember. And then these points are not as easy to remember, and they're easy to get mixed up. So, the basic way that, we have is if you can really remember what I tell students, if you can remember the square root of 1, then you're good. Because once you know the square root of 1, just continue the pattern. Square root of 1, square root of 2, square root of 3. Square root of 1, square root of 2, square root of 3. And then everything has a denominator of 2. And there you go. Now you just created it. Right? Because obviously a lot of students, when they're doing these problems, we're doing them quickly and they'll get them mixed up. And I do it all the time too. I might even do it today, right? You just got to slow down and think about what actually it is which angle and point you are using. Really the main confusion I would say what students have is mixing up the 30 degrees and pi over 6. But just remember, the larger the denominator, the smaller the fraction, right? So pi over 6 is smaller than pi over 3. But students just want to connect, the 6's together. Pi over 6 is 60 degrees and pi over 3 is 30 degrees, right? Just because there's 3's and there's 6's. But just remember, one is a measure and one is a fraction. So they are not equal to each other. So just make sure you're careful with that. And the other reason why I only rely on this first quadrant is because all the rest of these points over here, all of these points are just reflections. They're the exact same values. We're not like throwing a 4 in here or a 5 or a square root of 2 or a square root of 5 or a square root of 7. No, it's the exact same coordinate points. It's just reflections, right? It's just positives and negatives. That's all the only thing that's changing. So I have a step-by-step process to show us, how to use this circle and this right triangle. But the main thing is you need to know this first quadrant, because after we get into more advanced lessons in this course, we are going to rely on this, knowing the information on the first quadrant, because these are going to be coming up so often. We want to make sure that we know them and that we don't try to memorize something that looks like this. Now, I haven't actually done this in a long time, but I provided this actually to my students. So therefore, they could just see how everything is relayed. But I have been pushing for students to make sure they knew the first quadrant for so many years, because I see students that just get so dependent on using the unit circle and they can't think for themselves. They just anytime they have to, evaluate a trig function, they just automatically look at their unit circle. And then when it comes time for like a test or quiz and they don't have access to it, that's where they stumble. But this is the unit circle with all the values. And you can see trying to memorize something like this is crazy, right? Nobody wants to go ahead and do that. Yet memorizing something like this is really not that bad, right? And really my goal is not really to memorize anything, but it's just to keep on doing enough problems. So therefore you get really good at it and you basically kind of have it memorized by doing the work. But the main important thing is, well, why are we learning this again today, right? We already know sine. We already know these trigonometric functions. And you're right, like the sine in day 1 was opposite over hypotenuse. Did I already do this? No, I didn't. That's day 1. In day 3, we drew the triangles in the coordinate system, in the coordinate system, and therefore the sine of theta was the y coordinate over r, right? Still opposite over hypotenuse, but in terms of coordinate points, y or r, where r represented the distance away from the origin, which was also, known as the hypotenuse. So the nice thing here is if r is 1, I don't need to write it. That's why we just have sine is y, right? Like why write y over 1 when we could just write y? So that's kind of the nice thing about this is we don't really need to refer to 1. But the problem comes in is a lot of times, I'll give students a coordinate point. I'll say, evaluate the 6 trig functions. And like, for instance, they'll like take this point over here and they say, oh, the sine is the y coordinate, which is square root of 2. And it's like, no, remember guys, 45 degrees, like these coordinate points, this point, this point, this point, all have the same angle, 45 degrees. That means the sine needs to be exactly the same. So when the hypotenuse is 1, we know the sine is square root of 2 over 2, which we already knew from basic 45-degree triangles from day 1. So square root of 2 is not the sine of 45 degrees, right? It's the y coordinate over the hypotenuse. Square root of 2 over 2 is square root of 2 over 2. Here, square the y coordinate over the hypotenuse. So again, these points only work when you have a point on a circle with the unit circle, which we call the unit circle. So they only work is when we have a point on the unit circle. All right, so make sure if you're just taking the x and the y, or you're evaluating these new definitions, that you're only using them when you have points on the unit circle. And you can see 45 degrees for each of those is all going to be the same, square root of 2 over 2. One last point I would like to mention here is that the sine, theta equals opposite over hypotenuse. And the cosecant of theta was hypotenuse over opposite. Now, another way we could look at those reciprocals is just putting them over 1, right? Since y is over 1 here, we could just think of cosecant of theta as 1 over y. But that's important because, for instance, if I had the, square root of 2 over 2, I want you to understand that 1 over square root of 2 over 2, if you just put it under 1, that is the same thing as flipping it. Okay? So a lot of times in previous lessons, we just, flip the fraction. But this definition kind of looks like taking the sine, wherever sine is put in it under 1, which is, yes, that is correct. But don't forget like what we learned before, like the sine and the cosecant are reciprocals of each other. So if you have a fraction, or you can write the sine as a fraction or any trig function, a lot of times it's just going to be easier to reciprocate it to go ahead and get the value rather than putting it under 1. Because if you put it under 1, then, if you put it under 1, then you have the square root of 2 over 2. Then you're going to multiply by the reciprocal, which gives you now 2 square root of 2. So all I did was multiply by the reciprocal, which gave me back my answer anyways. So, a lot of people see these new definitions, and then instead of reciprocating fractions, they put it under 1 and they do this extra work. So I just wanted to kind of point that out. Last but not least, I wanted to point out one other thing is what about just like a random point? Like, we only have these points here. Why don't we have like a point right here? Actually, maybe I should just make sense of this. Like, why don't we have this point? Right? Where's that point? Like, what is that XY coordinate? And the thing is, well, we have that point. Like, you can actually evaluate that, but that's going to be some angle between 60 and 90. And that's not on our special right triangles. And for right now, we only know the sides of a triangle of our special right triangles. Those are the only triangles that we are referring to right now because we know them and we can use them without using a calculator. So, this could be, 70 degrees, 75 degrees, 80, like whatever it may be the case. But we will be getting with that, but that's going to be when we deal with calculators. For right now, we have these are all triangles. So therefore we can figure out what these coordinate points are. So that is what we are going to be using. So that is going to be for some later lessons. All right, so now let's get into some examples. Now, to evaluate the examples, we're going to look at the process. So the process that I have is for evaluating the 6 trigonometric functions given not a point, given an angle. All right, so the first thing we're going to do is we're going to sketch the angle in standard form. Then we're going to identify the reference angle. And again, these are all from day 2 in our lesson. Then we're going to determine the point given by the reference angle. So that is going to be, so basically we're looking at the point, and here's like, I think this is the important one. We're going to find the point given by the reference angle. Now, again, you might think of like, where's that point going to be, right? There's points in all of 4 quadrants. But if it's the point given by the reference angle, what is it we know about the reference angle? The reference angle is positive and then it's acute. That means the point of the reference angle has to be in the first quadrant. These are all basically our reference angles, right? Because reference angles have to be acute and they positive. That means it's going to be one of these. That's why I say only memorize these, because if you can figure out, what your reference angle is, you can find your coordinate point that you need. Then we're going to apply the sine based on the quadrant of the terminal side of the original angle to the point. Now that's a lot of words for really just saying apply the sine based on the quadrant the angle lies in. So obviously if the angle lies in the second quadrant, you're not going to, remember reference angle points are always positive. So if your angle though is in the second quadrant, you're going to make the x negative. If your angle lies in the third quadrant, then your point is actually, your x and y coordinates are actually both negative. And if your angle is in the fourth quadrant, then the y coordinate is going to be negative. So let me show you what I mean. And what I did is I kind of broke down each one of these steps and labeled them. Oh, I didn't finish these, I guess. So I evaluated 6 trig functions, I guess didn't finish it. So let's go ahead and do that. Did I not do? Yeah, I guess I just stopped. All right. So question number 1 is graph the angle. So I have 5 pi over 4, standard form, right? Going in the positive direction. Remember the reference angle is the distance away from the x-axis. So from here to here. And you can say that theta prime is going to equal, I wrote it up there, but theta prime is equal to pi over 4. Now you don't need to re-graph it over here, but again, I'm just showing you theta prime pi over 4, it's right there. That coordinate point is square root of 2 over 2, comma square root of 2 over 2. That is the coordinate point for the reference angle. You don't need to graph this, but I wanted you to see where I'm getting square root of 2 over 2. Yet, we know that the angle is in the fourth quadrant. So instead of using this point, we need to use this point where the x and the y are both negative. Now, again, we have an x and a y coordinate. We can use our new trigonometric function, our definitions. Sine is the y coordinate, cosine is the x coordinate. Tangent is the y over x, which is 1. Cosecant is, again going to be 1 over y, right? You could write it like this. But what I mentioned to you is why do that when all you need to do is just, again, reciprocate this. And then you'd rationalize the denominator in case you forgot. I'm going to not do this again. Because potentially I'm hoping that you just get used to these answers here, which is going to be a negative square root of 2. You can see that's like a lot of work. And thankfully, since I already did it once for cosecant, I don't need to do it again for secant because these are going to be the same answers, obviously. Same thing with tangent. Why flip this the other way? I know that the cotangent of theta is just going to also equal positive 1. So again, graph the point, find the reference angle, find the point of the reference angle, and then apply the signs based on the quadrant, and then you can evaluate your 6 trigonometric functions. So let's go ahead and do some more examples. So the first one here is 45 degrees. So what I'm going to do is I'm just going to kind of show you the angle. So 45 degrees is right there. The coordinate point here is square root of 2 over 2. Square root of 2 over 2. So here's the angle. Basically, I'm going to provide you with the point that I'm using. So that's square root of 2, comma square root of 2 over 2. Reference angle is obviously 45 degrees, so it's already in the first quadrant, so that makes life easy. And therefore, it's basically going to be the same answers that we just did. So sine of theta is going to be the y coordinate, square root of 2 over 2. Cosine of theta is going to be square root of 2 over 2. Tangent of theta is going to be 1, right? Because y over x is just 1. Cosecant of theta, you can reciprocate these, right? 2 over square root of 2. Hopefully you recognize that's just the square root of 2. Or you could do the secant of theta. You could say that's equal to 1 over 2 square root of 2. But again, when you do the math, you get square root of 2. And then the cotangent of theta is equal to 1. The next one, 5 pi over 3. So let's go ahead and graph that again. There we go. So 5 pi over 3, so that's going to be in positive form. So halfway from here to here is 3 pi over 3, right? So 4 pi over 3, 5 pi over 3. Again, if you're breaking things up into thirds visually. Let's just do this real quick, just for, because this one still gets students. 1/3, 2/3, 3/3, 4/3, 5/3. Okay, so you can see how that works there. So that's 5/3. Let's look at the coordinate points here. So in the first quadrant, the coordinate point for pi thirds is going to be 1/2 common square root of 3 over 2. But since we're in the fourth quadrant, the point that we're going to be working with is 1/2 common negative square root of 3 over 2. All right, so you see the difference? Like you can see the reference angle, and I guess I should probably write this. The reference angle is just going to be pi over 3. So therefore that coordinate point for pi over 3 is this, but then it's in the fourth quadrant, so therefore that's negative. So now we have the sine of theta. It's going to be negative square root of 3 over 2. The cosine of theta is equal to 1/2. And the tangent of theta is going to be negative square root of 3 over 2 divided by 1/2, which hopefully you should start getting used to. You could multiply. I'm going to show my work here so then I don't have to do this again. You can multiply by the reciprocal. That goes to 1. That divides out. Negative square root of 3. The cosecant of theta, let's just flip this. So that's going to be negative 2 over square root of 3. Rationalize the denominator. For the secant of theta, that's going to be 2 over 1, which is 2. And then we have the lovely cotangent of theta, which is equal to a negative 1 over square root of 3, which equals a negative square root of 3 over 3. Now, again, the important thing is, one thing I told students is when I'm looking in this fourth quadrant, I'm looking for your signs, right? I know that the y-coordinate is negative. That means sine, cosecant should be negative, and cotangent and tangent should be negative. Negative, 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 negative. But cosine and secant are going to be positive because they only deal with the x-coordinate and r, right? So therefore, those should be positive, which is good. All right, next one is 5 pi over 6. So again, that's going to be this angle right. No, don't do that. That's going to be that angle right there. We can say that theta prime is equal to pi over 6, which in the first quadrant, that gives us square root of 3 over 2, comma 1/2. Yet we're dealing with this point right here, which is going to be negative square root of 3 over 2, comma 1/2. So therefore, now let's go ahead and evaluate our 6 trig function. So the sine of theta equals positive 1/2. Cosine of theta equals negative square root of 3 over 2. And the tangent of theta is going to be the last one, 1/2 divided by, is going to be 1/2 divided by square root of 3 over 2. Now, I'm going to do this one more time. Multiply by the reciprocal. That goes to 1. The 2's divide out. You're left with 1 over square root of 3. Then you can rationalize the denominator. And you're going to get square root of 3 over 3. All right, I have now done the hard problem, so now I'm just going to give you the original ratio and then just move on. The cosecant of theta is equal to 2. The secant of theta, guys, we already did this, right? I already did this work. You flip it, so therefore it's going to equal a negative 2 square root of 3 over 3. All right, the last one is pi equals, or theta equals pi halves. So pi halves is right there, right? So this coordinate point is 0, comma 1. So again, what's nice about this unit circle, which actually I forgot to mention when I was doing more of the instruction, is now this doesn't create a triangle. We no longer need to rely on having a triangle to evaluate the 6 trigonometric functions. We can now evaluate these just based on a coordinate point on the unit circle. As long as we know the point is on the unit circle, we can apply those trigonometric definitions. So in this case, we have the sine of theta is equal to 1. Cosine of theta is equal to 0. And the tangent of theta is 1 over 0. Well, you can't divide by 0, so that's going to be undefined. So the cosecant of theta is 1 over 1, which is 1. The secant of theta, which is 1 over 0, which is, again, undefined. And the cotangent of theta is the x over the y, so it's 0 over 1, which is 0. So just remember, when we're dividing by 0, that's obviously going to give us a undefined value. But hopefully you guys kind of recognize here at least this process that I followed. And now we're just going to work through some more angles. For instance, negative angles. So again, when we do the negative angles, just remember we're going to be going in now in the negative direction. Doesn't change anything with our points. You know, obviously we're going to have different points here, but it doesn't make anything else negative, just changes our direction of our angle. So we go in the negative direction here. I have 0, comma, -1. I do not have a reference angle, but again, I don't need a reference angle because I already know the point on the unit circle. So in this case, cosine is 0, sine is -1, tangent is going to be y over x, which again is undefined. Secant is y over x, which is undefined. Cosecant is 1 over -1, which is -1, and cotangent is 0 over -1, which is 0. So let's go ahead and work through these. Again, really kind of the same process. So let's go and graph the angle, -π/6. That means this reference angle for π/6 is going to be π/6, which gives us, if you're going to find the coordinate point for π/6, that's going to be square root of 3. Come on. No, don't do that. Eliminate that. So it's π/6, so that coordinate point is square root of 3 over 2, comma 1/2. So that means this coordinate point, the one we're actually working on, is going to be positive square root of 3 over 2, comma -1/2. Okay, so the sine of π/6 is going to be -1/2. The cosine of π/6 is equal to the square root of 3 over 2. And the tangent of π/6 is going to be -1/2 over -1/2 over square root of 3 over 2, which I already solved, right? Where did I do that? It's one of these. Okay, I think I've solved all of these, so therefore now I'm just going to start giving you the answers there. So again, you can look at my work for previous to be able to figure that out. And that's going to be a negative square root of 3 over 3. Now, I do want you to understand that there's a difference here. Why am I using sine of π/6 instead of sine of theta like I did over here? Well, it doesn't matter. You can do anything you really need to. You can see that in each of these examples, my angle theta was defined, right? Or 45 degrees was defined as theta. So I just used theta, and I actually didn't mention that, and I kind of forgot about that, and I apologize, because you could say sine of 45 degrees, cosine of 45 degrees, tangent of 45 degrees, sine of 5 pi over 3, cosine of 5 pi over 3, tangent of 5 pi over 3. But even saying it is a lot. Writing it is a lot as well. The one thing you do not want to do is what one of my students asked me is, can we just like not write the thetas and just do sine, cosine, tangent? And I said, no, because remember, these are functions. They are functions of an angle. So if you don't have the function of the angle, then you are writing you're writing it completely wrong. So you have to make sure you have an angle. A lot of times students don't want to write the angle for every single time, so we just use theta. Sine, cosine, tangent. Therefore, the cosecant of π/6 is going to equal -2. The secant of π/6 is equal to 2 square root of 3 over 3. And the cotangent of π/6 is going to be reciprocal of that, which is just negative square root of 3. And again, this is in the fourth quadrant. So I know my sine and cosecant should be negative. My cosine, my secant should be positive. My tangent, my cotangent should be negative. Now, I wrote this because it wasn't really too bad to write π/6, but I'm not going to use -4 pi over 3. I'm just going to use theta in this case. Because again, remember, theta is equal to -4 pi over 3. They're interchangeable, right? So let's go and graph -4 pi over 3. So that's in the negative version. So here's 3 pi over 3, right? So -4 pi over 3 is right there. So again, we have a reference angle of pi over 3, which over here, pi over 3 gives us the coordinate points, positive 1/2, square root of 3 over 2. So over here, it's going to be a negative 1/2, comma square root of 3 over 2. And now we have our coordinate point in the correct quadrant. Let's evaluate the 6 trigonometric functions. So we have sine of theta, right? I don't want to use that. Sine of theta is, oh, I forgot to mention that though, didn't I? Did I mention that? Yeah, that was on there. Did I skip something? Hold on a second. I totally forgot to mention this. Oh my God. All right. I like skipped over this trigonometric functions. All right, let me go and do this, and I have one point that I need to mention. Sorry about that. So in this case, we have sine of theta. Sine of theta is equal to the y coordinate, which is square root of 3 over 2. The cosine of theta is equal to negative 1/2. The tangent of theta is going to be y over x, which is negative square root of 3. The cosecant of theta, which is going to be reciprocal here, which is 2 radical 3 over 3. You can see how I'm starting to do things a little bit quicker because it just is a lot to write. Secant of theta is negative 2, and it's the same thing over and over again, right? I don't need to show my work of simplifying the same problem 5 times. Like once you do it once, you have an example, and then we can just kind of repeat that. The cotangent of theta then is just going to be negative square root of 3 over 3. Now, let me go and take a quick, no, let's finish this one and then we'll go over. So then we have negative 3 pi over 4. Actually, I'll do that at the end. So let's do negative 3 pi over 4. So that's going to be right there, right? So the reference angle is going to be how far it is away from the x-axis, which is going to be pi over 4, right? Because if you travel negative 3 pi over 4, you need to go pi over 4 more to get to the x-axis. So that coordinate point is square root of 2 over 2, comma, square root of 2 over 2. Well, the point that we're working on is going to be negative square root of 2 over 2, comma, square root of 2 over 2. So let's go and evaluate these 6 trig functions. So the sine of theta, because I don't want to write negative 3 pi over 4 every time. The sine of theta is going to be square root of, that's both negatives. It's going to be negative square root of 2 over 2. Cosine of theta is going to be a negative square root of 2 over 2. And hopefully you remember this answer. The tangent of theta is going to be a positive 1. The cosecant of theta is going to be the reciprocal of that, which ends up being negative square root of 2. The secant of theta, which is the reciprocal of that, is negative square root of 2. And then last but not least, guys, the cotangent of theta is just going to be positive 1. So again, this is already some ratios that we've already simplified earlier. The only difference now is, you can see they're in the 4th quadrant, so we just want to make sure we have the correct signs. Last but not least here, we have a negative angle, negative 2 pi. So this one is going to be all the way around right there, which is going to produce this coordinate point 1, 0. It's not, it doesn't have a reference angle, right? The angle is 0, but we still need to evaluate here for the x and the y coordinate. And again, that's one thing I kind of forgot to kind of mention here is, when you're doing these, the reason why I'm evaluating these is because based on the x and y coordinates, right? These are the x and y coordinates that I'm using for each of these ratios. And I should mention that. At least in my examples. Did I mention that over here for the example? Yeah, I mentioned that for the x and y there. So at least I show my work, so that's at least good. All right, so now we have this coordinate point. Let's go and evaluate our 6 trig functions. So the sine of theta, you could use 2 pi. Let's just use, I don't want to use that. You could write negative 2 pi, right? But it's a little more. So sine of 2 pi. Oh, this is negative pi over 6, isn't it? That's why I don't like writing the angles. Because it's so much more work. Theta is much easier. So the sine of theta is negative 2 pi, which is going to be 0. The cosine of theta is going to be 1. The tangent of theta is 0 over 1, which is just 0. Let's see here. The cosecant of theta, which is 1 over 0, which is undefined. I don't really like how that's out of the way now. The secant of theta, which is 1 over 1, which is 1. And the cotangent of theta, which is 1 over 0, which is, again, undefined. Okay, so you can, again, see when you have these coordinate points on the axes, you're going to have some undefined values. All right, last but not least here, our last round of examples is going to be angles that are larger than a revolution. So what I did is I kind of did this a couple ways. First way was the old school way, the way that I first taught you how to graph angles in day 2, which is basically like take the circle or take half a circle pi, right, and break it up into 3 parts, 3 pi and 6 pi, right? Break it up into fractions, and then you can just count, right? So we go all the way around. This is negative, right? So it's negative 3 pi over 3, negative 6 pi over 3, negative 9 pi over 3, negative 12 pi over 3, negative 13 pi over 3, negative 14 pi over 3. And you can see that it's kind of like a lot of work. And especially like, what if I gave you something like 148 pi over 3? You're not going to want to count to, 148 to graph the angle. So one thing we can do is use period as an aid, use an extra revolution. And so what's happening here is if you look at this graphically, I went around the circle once, and then I went around the circle again. And then I went around the circle negative 2 pi over 3. So obviously, this angle and this angle are not the same, right? If you run around a track, you want credit for running around the track. Yet you begin and you end at the same places, right? You start here, you end here. You start here and you end there. So therefore, these are coterminal angles. And what's important about these is what I wanted to discuss earlier, is that they have the same coordinate point on the unit circle. Therefore, their 6 trigonometric functions are the same. So while if I ask you to graph this, you need to make sure you have those extra revolutions, when we're looking into evaluating the 6 trigonometric functions, we don't care about these extra revolutions, right? We don't care about negative 6 pi over 3 going around twice. We just want to know, where are you ending up? Which quadrant are you ending up on? What is the reference angle where you ended up on? So we can evaluate the coordinate point. Again, you can see right here, negative 14 pi over 3 and negative 2 pi over 3 are coterminal. They have the same initial and terminal side. So therefore, since they're coterminal, they're going to have the same reference angle and the same coordinate point on the unit circle. But again, since they're in quadrant 3, therefore we're going to be using negative 1/2 and negative square root of 3, right? So again, you could do this, the graphical approach. I prefer just to find a revolution, right? We know that 2 pi in terms of thirds is equal to 6 pi over 3, right? So therefore, the hard part about this problem was it's negative. So you don't want to add 6 pi plus 6 pi. You got to use negative 6 pi over 3 because you're using the negative direction. And then when you keep on finding them, you basically just find the remainder, and that's going to be your coterminal angle. So therefore, I have, in this case, negative square root of 3 over 2, negative 1/2. I simplify. And again, you see in the third quadrant. So sine, cosecant, secant, and sine, cosine, cosecant, and secant should all be negative, which I forgot to write a negative there. See how that's a good check. Yet tangent and cotangent should be positive, which they are. Okay, so that's really the only difference. What we're going to do is just kind of rewrite these. You could graph them, and I'll graph them. That's, fine. But I am going to also just kind of rewrite the angles so therefore we can better understand them. So 13 pi over 3, we know all the way around is 12 pi over 3 plus an extra pi over 6, I'm sorry. The nice thing, though, is that gives us a point in the unit circle, right? So that's 12 pi over 6 plus pi over 6. Right? So we can cancel out that extra revolution if we wanted to. Theta prime equals pi over 6. Well, our coordinate points for that is going to be square root of 3 over 2, comma 1/2. So we have the sine. Again, I don't really want to write 13 pi over 6, so I'm just going to use theta. Sine of 13 pi over 6 is 1/2. Cosine of 13 pi over 6 is square root of 3 over 2. And the tangent of theta is going to be y over x. So that's going to be 1/2 over square root of 3 over 2, which when you simplify will give you square root of 3 over 3. For the cosecant of theta, that's going to be 2. Secant of theta is going to be 2 radical 3 over 3. And the cotangent of theta equals the square root of 3. And again, everything's positive because we know it's in the right quadrant. I'm not showing a lot of my work here because I've already showed the work, right? All right, let's go ahead and graph negative 420 degrees. Well, negative 360 is right there, right? So then I need to add another 60 degrees to get me to that. Or you could just write this as negative 360 degrees plus negative 60 degrees. Right? And therefore we recognize then since we went 60 degrees past the x-axis, our reference angle is going to be 60 degrees. So therefore the coordinate point at 60 degrees is 1/2 square root of 3 over 2, but that's in the first quadrant. We are in the fourth quadrant, so therefore my y coordinate is going to be negative. So now let's evaluate the 6 trig functions from here. So we'll have the sine of, I don't want to write negative 420, so I'm just going to use theta. So the sine is going to be negative square root of 3 over 2. Cosine of theta is 1/2. Tangent of theta is now going to be sine over cosine, so now it's the flip version of that, which is just going to be square root of 3. Yet it's in the fourth quadrant, so it's a y over a negative, so that's a negative square root of 3. The cosecant of theta is, again, we already know that reciprocal, so that's going to be negative 2 square root of 3 over 3. The secant of theta is going to be a positive 2, and the cotangent of theta is going to be the reciprocal of square root of 3, which is square root of 3 over 3. There you go. All right, let's do another one, 11 pi over 4. So 11 pi over 4, it's going to be in the positive direction. Well, here is 8 pi over 4, right? And then you could do 9 pi, 10 pi, 11 pi. 11 pi right there. So an extra 3 pi over 4. All right, or we could just write that as a revolution. 8 pi over 4 plus 3 pi over 4. From there, we recognize that the reference angle is going to be pi over 4. So the coordinate point over here is going to be square root of 2 over 2, comma, square root of 2 over 2. Therefore, for this point, it's going to be a negative square root of 2 over 2, comma, positive square root of 2 over 2. So now let's just evaluate the 6 trig functions. So again, we have sine of 11 pi over 4, but let's just use theta. That's going to be a positive square root of 2 over 2. The cosine of theta is going to be a negative square root of 2 over 2. And the tangent of theta is going to be y over x, which is now going to be a negative 1. For the cosecant of theta, that's going to be the reciprocal, which hopefully you remember is square root of 2. The secant of theta is that reciprocal, but in this case it's negative since it's in the second quadrant. And the cotangent of theta in this case is going to be, obviously, again, another negative 1. All right, in the last case here, again, we have 3 pi, so that's going to be all the way around the circle is 2 pi, and then we're just going to go an extra pi, which gives us to our point negative 1, 0. Or you could also write this as 2 pi plus pi, right? You did the extra revolution, but then you're back there. All right, so we have our coordinate point, no reference angle. So the sine of, let's just write it as 3 pi. That's not too hard to write, right? The sine of 3 pi is 0. The cosine of 3 pi is going to be negative 1. And the tangent of 3 pi is going to be 0 over negative 1, which is 0. The cosecant of 3 pi is going to be 1 over 0, which is obviously undefined. The secant of 3 pi is going to be 1 over negative 1, which is negative 1. And the cotangent of 3 pi is going to be negative 1 over 0, which again is going to be undefined. Now, before I get to the final reflection, I just wanted to kind of highlight this slide that I did not talk about that I showed some work on. And this was something before the process, because this is one of those this is something I wanted you to take away from this. So before I actually gave students a process, I said, why don't we graph the angles, find the reference angle, determine the quadrant, and then determine the point on the unit circle. So we actually practiced this before we went into the problems. And the point that I wanted to make with the students was that, you know, here the reference angles are the same. Pi over 6 and 5 over 6 have the same reference angle, right? And since they have the same reference angle, the coordinate points are the same. And since their coordinate points are exactly the same, you can see that the only difference is, again, the signs based on which quadrant they're in. But in this case, you can see that the sine is both the same of 1/2. So what that really means now is that the sine of pi over 6 is equal to the sine of 5 pi over 6, right? All the other trigonometric functions are going to be different signs. But for these two angles, you can see that the sine is equal to each other. In this case, in the second and the third quadrant, you recognize, again, same coordinate points, same reference angle. The only difference here is the y coordinates, because one's, in the second, one's in the third. But the cosine is the same for both of them. So therefore, the cosine of 2 pi over 3 is equal to the cosine of negative 2 pi over 3. Because, again, the only difference is, there is no difference with the cosine. They're both in negative 1/2. And then we look at these two triangles. Again, they have the same reference angle, so therefore they have the same coordinate points. They're in different quadrants, so this is positive, positive. This is negative, negative. But again, the tangent is going to be the same for them. So therefore, the tangent of negative 3 pi over 4 is equal to the tangent of pi over 4. So that's that kind of relationship that I just wanted students to understand. If you understand the quadrants that they're in, you understand these positive and negatives of these points, you're going to understand that relationship for the trigonometric functions. And then last but not least, the most important one is 90 degrees and 450 degrees. Those are the exact same points. Those are coterminal. And this is something that we investigated on our own because we didn't talk about it before. But of course, guys, coterminal angles, since they have the same coordinate, since they start and end at the same spot, they're going to have the same coordinate point on the unit circle, and therefore the 6 trigonometric functions are going to be exactly the same. That's why it was so important in our last example just to find a coterminal angle that worked for us, because you could use these large angles, but if you just use period A's to reduce them to a coterminal angle that we're more familiar with, it's a little bit easier to evaluate the unit circle, define the reference angle, and so on and so forth. But again, guys, hopefully from this lesson, you understand a little bit more about where these points come from on the unit circle. They're not just made up points. They come from special right triangles they come from special right triangles placed on a coordinate grid when the hypotenuse is 1. And again, since the hypotenuse is 1, our trigonometric functions now can just be the coordinates of those coordinate points. We don't need to include the hypotenuse any longer for our definitions, which makes everything a little bit easier and more efficient when evaluating the 6 trigonometric functions. So hopefully you guys enjoyed. If you have any questions from this lesson or some things that you would like a little more clarifications on, please feel free to comment down below, and I look forward to seeing you guys on the next video. Cheers.